The electric flux across a surface is given as the integral of the dot product between the electric field and the area differential for an element of that surface. Let's break down each of these in turn. Earlier we said that the electric field, or the electric flux rather, is proportional to the number of electric field lines. That proportionality is given by this integral above. Let's take a look. Let's start with the fact that we know then from our previous discussion that electric flux depends on three things. It depends on the magnitude of the electric field. It depends on the size of this area. And it depends on the orientation of the electric field vector with the area. And I should add with the area vector. Well, let's look at each of these in turn, beginning with the fact that the electric flux is proportional to the number of field lines, and that proportionality is going to depend on the magnitude of the electric field. To evaluate that, let's draw a two-dimensional surface defined by this area vector being equal to the product of an area and a vector normal to the surface. For perspective, our coordinate system is a three-dimensional rectangular coordinate system. Let's look at an electric field. Here is a single electric field vector passing through the surface. This electric field vector, the way I've drawn it, is perpendicular to the plane of the surface or parallel to the area vector describing the surface. This single electric field vector represents, or this single electric field line provides a visual representation for the magnitude of an electric field. Because as you know, electric field lines, the density of electric field lines models the strength of an electric field in a region of space. Right now, we have one field line passing through the surface. I'll call the amount of flux in this picture right here, we'll just say this is an amount of flux, which I will call phi1, one field line passing through that surface. Let's add another field line. Two field lines passing through the surface. So the flux represented by this is now double than what it was before. Two field lines, same area, same orientation, the flux is doubled. Now let's add a third field line. The flux has now tripled over what we had before. Now remember, the density of electric field lines correspond to a model for the strength of the electric field in that region of space. The greater the number of lines, the greater the magnitude of the electric field. Now that we have three lines here, the magnitude of the electric field has tripled over the first image in which we had just one electric field line. Now, not only that, there are 3 field lines passing through the surface. That means the electric flux has tripled as well. So if we continue adding field lines, now the flux is quadrupled from what we originally had. Now the flux has increased to 5 times from what we've originally had. So notice the magnitude of the electric field in this region of space, indicated by the density of the electric field lines, is proportional to the number of field lines passing through that surface. So this is why we could say that electric flux is proportional to the number of electric field lines, and that proportionality is partially dependent on the magnitude of the electric field. The greater the magnitude of the electric field, the more field lines we have passing through the surface. Let's now look at a uniform electric field in space. We can tell that this electric field is uniform because the electric field lines are parallel to each other. Because they're parallel to each other, the density of the electric field in any portion of space remains constant. Let's look at a surface oriented like so. This surface is described by an area vector that is normal to the surface. Notice that there are 5 electric field lines passing through that surface. And notice that the electric field is also parallel to the area vector. What if we use a smaller surface, oriented just the same? What if our surface was this big? I'll just call this area 2. And I'll call the first one area 1. Well, notice we now have only 3 electric field lines passing through surface 2, while we have 5 electric field lines passing through surface 1. Because there are 5 electric field lines going through surface 1 and only 3 electric field lines going through surface 2, we can say that the electric flux through surface 1 is greater than the electric flux through surface 2. Let's do a third surface with the same orientation as the other 2 surfaces, just smaller. So this third surface has an area vector, and really I should have been drawing these area vectors proportional. So I'll go back and just quickly sketch a more proportional set of area vectors. So for this first surface, I'll keep the first surface's area like that. For the second surface, I'll just draw an area vector a little smaller. And for the third surface, the area vector should be smaller still. What do you notice between these 3 surfaces? Well, you notice that in surface 3, only 2 electric field lines are passing through the surface. So through surface 2, 3 electric field lines are passing through the surface. Through surface 1, 5 electric field lines are passing through the surface. Which means that the electric flux for surface 3 is smaller than the electric flux through surface 2, which is smaller than the electric flux through surface 1. So from here, it's clear that electric flux is also dependent on the area of the surface through which the electric field vectors pass. Let's now look at the same electric field, but let's change the orientation of the area with the electric field. Let's have an area that looks like this to start. Or a surface, rather, that looks like this to start. Let's have a surface that looks like this to start. Notice that there are 3 electric field lines passing through the surface, and this surface is described by an area vector normal to the plane in which the surface lies. In this, notice that the area vector is parallel to the electric field. Well, what if we change the orientation of our surface? Let's angle our surface such that its orientation is like this relative to the electric field. So the surface has the same area. We didn't change the size of the surface. All we did was change the orientation of the surface with the electric field. Let's call this situation 2, and the first one we'll call 1. In 2, there's only 1 electric field line passing through the surface, while in 1, 3 electric field lines are passing through the surface. Because there are more field lines passing through the surface for 1 than in 2, we know that the electric flux through surface 1 is greater than the electric flux through surface 2 because the electric flux is proportional to the number of electric field lines. So we've changed the angle. And let's look at that angle. So if we just put an electric field vector, we will say, I'll just put an electric field vector right here for reference. If we look at the angle between that vector and the area vector, that is given by the angle theta. I'll just call this angle theta EA for the angle between the electric field and the vector. Notice that is a non-zero angle here, while in the first one here, if I just draw my electric field vector right at a point on the surface, I will call that our electric field at that point. In this first situation, I'll call this first situation theta EA1 is 0 degrees. The angle between the area and the electric field is 0 degrees. While the angle for the electric field While the angle between the electric field and the area vector in situation 2 is some angle less than 90 degrees, but that angle is not 0. Now let's look at a third situation in which we rotate the original surface by 90 degrees from its original orientation. That means the area vector is pointing straight up. The size of the surface hasn't changed, only its orientation. The electric field is still pointing to the right. And so notice there is an angle of 90 degrees between the electric field and the area vector. Also notice that 0 field lines can pass through that surface when the area vector is perpendicular to the surface. So since 0 field lines can pass through that surface has 0 electric flux, which means the electric flux through surface 3 is less than the electric flux through surface 2 is less than the electric flux through surface 1. Now, the only thing we varied here was an angle. We said that when the angle was equal to 0 degrees, we had the most amount of flux. However, when the angle was equal to 90 degrees, we had 0 flux. And when the angle was somewhere between 0 degrees and 90 degrees, we had some amount of flux. Can you think of a trigonometric function that is a maximum when that function evaluated at the angle of 0? Can you think of a trigonometric function that is a maximum at 0 degrees, a minimum or 0 at 90 degrees, and some value between a maximum and 0 for an angle between 0 and 90 degrees? If you said cosine, you'd be absolutely right. You know that the cosine of 0 degrees is 1. The cosine of 90 degrees is equal to 0. And the cosine of some angle between 0 and 90 degrees is going to be a value between 0 and 1. The greater the angle between 0 and 90 degrees, the smaller the flux, as you could see here. When our angle was 0 degrees, we have maximum flux. When our angle was 90 degrees, we had 0 flux. When our angle was in between 0 and 90 degrees, we have some flux. This means that we could say that the orientation of the electric field and the area vector influences electric flux. So when we say that the electric flux is proportional to the number of field lines crossing through a surface, the number of field lines that cross through the surface depend on the magnitude of the electric field, the size of the surface, and the cosine of the angle between the electric field and the surface. And this is why we can define electric flux as the surface integral of the electric field.